Hi everyone, welcome to my YouTube channel Nature's Language. Today we are going to see how quantum mechanics actually came into picture or how it was started. Hmm, In the past, people always wondered what is light actually, but they didn't know the answer to it. Then Newton, who was like godfather at that time, said that lights are like particles, and those particles are move everywhere. The particle moves everywhere and strike the surfaces and bounce back, and that's how he explained the reflection property of light. And one day someone asked him that, oh, so why lights, some lights are colored. So he answered that light may be consists different particles of different colors, that's why they are colored. And that hypothesis known as corpuscular model, which continued to um, continued to evolve over 100 years. But then Huygens proved that wrong, and he established the um, wave nature of light. And also Maxwell's electromagnetic theory proved that light is an wave. But in the year 1900, the study of blackbody radiation couldn't be explained by EM theory, which led to Planck, who was the father of Persian Academy at the time, to suggest that the lights or radiation consist of discrete energy particles or quantum particles. But he at that time he didn't believe himself. He thought that this is just a mere mathematical trick to solve the problem. But Einstein believed him so much that he took that hypothesis and applied it to photoelectric effect. And it was very easy to explain photoelectric effect with the help of um, quantization of energy. And in 1924, Compton effect experimentally proved the existence of photon with discrete energy h nu. And so the blackbody radiation was a stepping stone for quantum mechanics, where the light was considered as discrete flux of particles and each having energy h nu, where h was the new constant, which is known as the Planck's constant, and this is the value written on the screen, and nu is the frequency of that radiation. So E equals to h nu, or h cut omega, is known as the Planck-Einstein relation, where h cut is the reduced Planck's constant, or h by 2 pi. Omega is the angular frequency, or 2 pi nu, of the incident wave or radiation, and then k is defined as 2 pi by lambda, which is the wave number and whose direction is the same as the propagation as the direction of propagation of the wave. And a new term was defined, p, which is the momentum and is given by h cut omega. So here energy and momentums are the particle parameters, and nu, omega, k, lambda, these are wave parameters. Then Young's double slit experiment show us a very important observation. So this figure is schematic diagram of Young's double slit experiment, where there is two slits F1 and F2, and if we block the slit F2, we can see a intensity say I1 because the slit F1 is open, and if we block F1 we see a intensity I2 because slit F2 is open. But when we open both the slits, we didn't see the intensity as I1 plus I2. But if light is a particle or flux of particles, then we should get the intensity as I1 plus I2. But we see a interference pattern consecutive dark and bright fringes, which cannot be explained by particle model of light. We need wave aspects. But again, only the wave nature of light cannot explain this experiment, because if we use a very weak source of light, say which is generating about 1 photon at a time, and we conduct this experiment, so we can see some discrete patches on the screen. But if light is a wave, no matter how weak the source is, we must see a distribution or the fringe pattern on the screen. But we can see that when we do this experiment with very weak source. So only wave nature of light cannot explain the experiment, and only particle nature of the light cannot explain this experiment. So after very rigorous arguments and experiments, scientists came into the conclusion that light behaves as particle as well as wave. Thus the dual nature of light was established. So purely wave and purely particle nature of light couldn't explain this behavior, and we must reject both of them. And in that experiment, if we perform the experiment for a very long time with very weak source of light, we can eventually see the interference pattern. So we can say that particle and wave aspect of lights are inseparable. Light behaves simultaneously like a wave as well as a flux of particles. And the prediction about the behavior of photon can only be probabilistic. We can't definitely say that this is where the particle is going to hit. We cannot say that. We can only give a probability. And how can we check the probability? Only if we make a number of identically prepared systems and then perform the same experiment on those systems, then we can see that yes, our prediction is right. It is following the probability. So thank you very much. See you in the next lecture. Please subscribe my channel and share it with your friends. Thank you.